Wow, you guys got in so fast. All right, sorry the link was so late getting up. My Calc 1 class today was learning about derivatives of trig functions. I don't know if you remember the geometric arguments that are involved there, but trying to hold hands through that can be a little bit time consuming. So thank you guys for your patience. Let me get things oriented here for you. All right. So a reminder, exam 1 is 1 week from today. I will be posting the study guide today and detailed instructions for both the study guide and exam 1 to Canvas. So watch the Canvas announcements a little bit later in the day, and you will see some very detailed instructions, exactly what I want you to do for the study guide, exactly what you're required to do for the study guide, and then what you're required to do for exam 1. Lately, we've been talking about trig sub, and then we also need to talk about partial fractions. So I think we've done probably enough trig sub. I would be okay with doing maybe one more example, but the partial fraction stuff takes a little bit of time to get through. So I want to spend the bulk of our class time on that today. If there is maybe a trig sub problem that you guys would like to look at before we dig into the partial fraction stuff, I would be willing to do maybe just one trig sub example here before we get into that stuff. So is there anything in particular from the trig sub homework that you guys would like to look at before we move on from section 7.3? Number 2. Okay. So, all right, that's what we will do then. Just a quick reminder, you do want to be finishing up with homework 4. We should all be done with homework 4 by today. It is due today. We extended it from Monday, and you really do want to be done with that so you can be working on homework 5 over the weekend, and that will give you most of next week to worry about the study guide. Now, I know there's some stuff in homework 5 that we haven't talked about yet, namely the partial fractions. We'll be sorting that out today. Number 2. Yeah, this is a good one. So this is another example of a trig sub integral that doesn't have at least an obvious square root in it, although it does have a rational power, where the denominator is 2, which is the same as the square root. So, excuse me just one second, and we'll dig into that problem. Coffee. Water. All right. So this is homework 5, problem 2, and we want to do the integral from 2 to somewhere, 2 to 5, of 1 over x squared minus 1 raised to the 3/2 power. All right, so this is our goal. my denominator, I could, if I wanted to, rewrite as the square root of x squared minus 1 cubed. So if you're having a hard time spotting the substitution, that might help you spot the substitution. That shape, square root of x squared minus 1, tells us that we should substitute for secant. So this will be a secant substitution. X equals secant theta, which means dx will be secant theta tangent theta d theta. And then I do need to change my bounds. And here this could be a little bit unpleasant, especially depending on what your upper limit is. So let's handle the lower limit first. When x is equal to 2, that means 2 is equal to secant theta. And while you might not remember the inverse secant of 2 off the top of your head, if you rewrite that in terms of cosine, that means cosine theta is 1/2. And the inverse cosine of 1/2 is something you should know. What is the inverse cosine of 1/2? For what angle between 0 and pi is cos theta equal to 1/2? Yeah, pi over 3, bueno. Now for my upper bound, when x is equal to 5, and this is the part that's randomized by WebAssign, so you might have a different number, I'm not going to have a beautiful way of writing this. I'll say, okay, well 5 is secant theta. Therefore, there's a few ways to write this. I could say theta is the inverse secant of 5. That's one option. Or if I wanted to write this in terms of cosines, I could say that this is the same as saying cos theta equals 1/5. So I could also call this the inverse cosine of 1/5. And it's up to you how you want to express it, but I would leave it as one of those two things. At the end, we're going to have some simplification to do, and one of those forms might be more useful than the other. It's hard to anticipate right now, so I'll write both. But when I write the integral, I'll be writing my upper bound as the inverse secant of 5. So I have integral pi over 3 to the inverse secant of 5, 1 over x squared, that's secant squared theta, minus 1 raised to the 3/2 power. Zoom in just a little here, there we go. And then my differential term, don't forget your differential term, dx is secant theta tangent theta. If you leave that off, then this is really unpleasant. From here, I have the integral from pi over 3 to the inverse secant of 5, secant theta, tangent theta, all divided by secant squared minus 1 is tangent squared, raised to the 3/2. This camera doesn't want to focus today. There we go, that's better. Okay, tan squared theta raised to the 3/2. This is tangent theta all squared raised to the power of 3 over 2. That's tangent raised to the 3/2 times 2, which is tangent cubed. So this is secant theta over tan cubed theta d theta. And from here, I don't see an obvious path, not with it written like that. So I'm going to want to rewrite my integrand. Oh, okay. This is maybe the catch then. So tan squared theta, I'll come off here for a second. Raised to the 3 over 2. Remember what tan squared means. This is tan theta all squared raised to the 3 over 2. Tan squared theta is tan theta squared, right? It's the square of the tangent of theta. So if I wanted to be really careful, it's like this. Can everybody see that? It's not the theta that's being squared, it's the tangent that's being squared. That's why we normally write it as tan squared theta. This paren here closing this paren here. And then we have this rule for exponents that says if you raise one thing, so if I have like x to the a all to the b, that's the same as x to the a times b. So that means that this, I'll write it down here, is the same as the tangent of theta raised to the 2 times 3 halves. And 2 times 3 halves is 3. So this is tan theta to the 3, or tan cubed theta. So maybe this was the sneaky part. In any case, this is where we land. Was there a tangent in the numerator that I lost? Oh shit, you're right. You're right. Sorry. Secant theta, tan theta, d theta. Thank you. Yeah, so the top is secant tangent, and the denominator is tangent cubed. Thank you. Caught that just in time. I was just about to mess up. So I get the integral from pi over 3 to the inverse secant of 5, secant theta tangent theta over tan cubed theta. I can cancel one of the tangents, and that's secant theta over tan squared theta d theta, like this. Yeah, good catch. All right, so what do I do with this thing? Yeah, the easiest way to see what to do here if you're having a hard time is to rewrite everything in terms of sine and cosine. So if I wrote it as secant times cotangent squared, that wouldn't really help me see what to do. But if I rewrite everything in terms of just sine and cosine, that's kind of the most natural thing. Secant is 1 over cosine theta. And I'm dividing that by tan squared theta. So that's 1 over sine theta over cos theta squared, like this. I'll write it like that for now, so everybody can see where we're going. This is multiplication here. So I'm thinking of this as secant theta times 1 over tan squared theta. So my 1 over cos theta is going to hang out. And then sine theta over cos theta squared downstairs is the same as cos squared theta over sine squared theta, like this. So I can cancel one of the cosines. And I'm left with cosine over sine squared. And this is a good candidate for a little substitution. Or if you're feeling extra sneaky, I do see something else. Does anybody else see another way to tackle this? U sub will work. Sine squared is the same as 1 minus cos squared, but that wouldn't be as nice. There's an extra sneaky approach here. Would you believe me if I told you this is the same? Cosine over sine is cotangent. 1 over sine is cosecant. This is cosecant theta times cotangent theta. You could also U sub. Nothing wrong with a U sub here. Yeah, the cosecant cotangent thing is extra slick because this will get us there even faster. So the U sub thing works great. Don't hesitate if you want to do the U sub, right? You can let z be sine theta, dz is negative cos theta d theta. You get the integral negative 1 over z squared dz, which you would integrate as a power rule thing, and it'll come out nice. But if you want to be even lazier, then this will work also. So 1 over sine theta times cosine theta over sine theta. That's cosecant theta times cotangent theta, which is the derivative of negative cosecant theta. And we're still going to have to handle that inverse secant of 5. That's still going to be a little bit tricky, but we can do it. It's not too bad. So let's take a second, regroup, make sure we're comfy up to here. There's kind of 2 little things that were funny there, maybe completing the, or understanding the tan squared to the 3/2 piece, and then also this funny business, rewriting cos over sine squared as cosecant cotangent. Again, the substitution would work fine there also. If you let u or z be sine theta, then the integral here can certainly be handled with another substitution. It's just that changing that bound is not going to be fun. Shit, this chair's rough on my back. All right. So from here, what I need is the negative cosecant of the inverse secant of 5 minus the negative cosecant of pi over 3. Cosecant is the reciprocal of sine. Recall the sine of pi over 3, that's root 3 over 2. So cosecant of pi over 3 is 2 over the square root of 3. Cosecant's the reciprocal of sine. So this piece right here is 2 over root 3. I still have to deal with the negative cosecant of the inverse secant of 5. I'll show you how to do that in a second. But these 2 minuses make a plus, and we get plus 2 over root 3. All right, who loved trigonometry? Who remembers how to handle shit like this? Have any takers on this one? see some stuff in chat here. That's okay. So the trick is to draw a triangle. To simplify, forget about the negative just for a minute. The cosecant of the secant inverse of 5, we let theta, or I should use a different variable here, let phi be the inverse secant of 5. That means the secant of phi, or phi, is 5. Another way to say that is the cosine of phi is 1/5. And I interpret that geometrically. Cosine is the adjacent over the hypotenuse. So I'm going to draw a triangle. So if I draw a little right triangle there where the internal angle is phi, oh no, trig is all of math. Yeah, that's maybe a little bit too much, but trigonometry is your friend, and we're going to have to become friends with it to survive not just this class, but also Calc 3, differential equations, pretty much everything. I recognize that it's different than the algebra that we do a lot of the time, but it is super important. So let's be brave. My adjacent side I label as 1, my hypotenuse I label as 5, and then I complete this side of the triangle. This squared plus this squared equals this squared. So this guy is 25 minus 1 under a square root. That's the square root of 24. And now remember what it is that I'm after. Cosecant of the inverse secant of 5. Well, this angle phi is the inverse secant of 5. So that's just the cosecant of phi, which I can now read off of my completed triangle. Cosecant is the reciprocal of sine. That's the hypotenuse over the opposite. Which is 5 over the square root of 24. So there's all that little bit of side work for simplifying that piece. And finally, I'm able to write my integral as the negative of cosecant of inverse secant of 5. That's the negative of 5 over the square root of 24 plus 2 over the square root of 3. A word of warning, the exam that we're going to take next Friday is definitely going to require trigonometric manipulations on this level, right? This is the same thing as like the triangle you draw in the indefinite integrals, just with particular numbers plugged in. There's nothing here that is especially heady, but you do need to know your unit circle. You need to be very comfortable with the definitions of the inverse trig functions. All of that stuff is super duper important. So if this is something that's like scary, then this is stuff that maybe we want to talk about in office hours, stuff you want to focus on in the study guide, that sort of thing. So from here, we're done. This is it. Yeah, this is the problem. So the last section that we need to cover or talk about is section 7.4. Is on partial fractions. And ideally, I would be able to say everybody learned partial fractions way back in pre-calc, and so I'm just going to rush into this, but that would be a horrible thing to do because not everybody learned partial fractions in pre-calc. Partial fractions is an algebra thing. It's not a calculus thing. We use it in the same way we use trig identities to help us with certain integrals, because it lets us rewrite integrands, the things we're integrating, in a way that makes them easier to integrate. It's used exclusively on rational functions. What it does is it gives you a way to take an arbitrary rational function and split it up into simpler rational functions using the factors of the denominator. So recall, a rational function is one of the form usually write r of x equals p of x over q of x, where, and this is important, p and q are polynomials. So no square roots of x, no e to the x, no sine x or cos x. P and q must be polynomials. There's a definition that I need you to internalize. A rational function r of x equals p of x over q of x is called proper if the degree of the bottom is strictly bigger than the degree of the top. Okay, so this notation deg stands for degree. Remember, the degree of a polynomial is the largest power of x that shows up in that polynomial. The procedure called partial fractions can only be applied to proper rational functions. Fact, if a rational function is improper, meaning it's not proper, meaning the degree of p, the degree of the top is greater than or equal to the degree of the bottom, we can long divide. To write it as a sum of polynomials plus a proper rational function. Sorry, camera here. Okay, so if I hand you an integral of a rational function and you want to do partial fractions on it, first you need to check whether or not that rational function is proper. We can only do partial fractions on proper rational functions, meaning the degree of the bottom is bigger than the degree of the top. If the degree of the bottom is not bigger than the degree of the top, meaning the degree of the top is bigger than or equal to the degree of the bottom, then you need to start by long dividing. And if you don't remember how to long divide polynomials, I'll do an example, and also I'll post a little thing to Canvas under our modules to remind you how that goes. But anytime you're given an integral where the integrand is a rational function and the degree of the top is bigger than or equal to the degree of the bottom, your very first step should be long divide. So with that said, here's how you do partial fractions. It's a little bit complicated. If you look on the Wikipedia page, the full rule is terrifying, right? To write it all out in a single statement is not an easy thing to do. I don't suggest doing that. We break it down into cases. So first, is the rational function proper? If no, long divide and come back. 2, factor the denominator. What we will do depends on the factors of the denominator. 3, write down what we're going to call the PFD setup, partial fraction decomposition setup. And this is based on the factors of the denominator. So most of what I'm going to show you today is how to use or how to pick the PFD setup. Okay. Once you have your PFD setup, so don't worry about how to pick the PFD setup or even what this means for now. Just follow me in these notes, write these things down. This is your high-level strategy. Then you're going to solve for the missing coefficients in the PFD setup. Then you'll rewrite your integrand, rewrite your integral. So all of this is going to be done outside of the integral. We don't fuck with the integral at all in steps 1 through 4. Once we've completed the PFD, meaning we solve for the missing coefficients in the PFD setup, you'll rewrite your integral and calculate the antiderivatives. Okay, so I know right now we don't know what some of these things mean. I'm going to explain them to you, but please get this in your notes so you have a skeleton on which to start building. Your PFD setups will depend on whether your denominator has any repeated factors, whether it has any irreducible quadratic factors. Sorry, I'm not upstairs today. I'm in my living room downstairs, so my dog needed to go outside. I apologize. So what is PFD? PFD lets us take a rational function and split it up into smaller, simpler rational functions. Each one is very easy to integrate. It's kind of like going backwards in the process for finding a common denominator. So I want to show you an example of what it is I'm talking about here, and that will help you to start to gain a little bit of intuition. Again, this is just algebra. So if I have the rational function 1 over x squared minus x, I'll call this r of x. That is a proper rational function. So I will factor the denominator. These are the factors of that denominator, right? X and x minus 1. It is a fact coming from a field of mathematics called linear algebra, which talks about how to write things as combinations of other things. You may have heard that term in your pre-calculus class when you learned about matrices. A matrix is a combination of vectors. It turns out that there's a lot of shit that can be vectors. We talked about that last time. Functions can be vectors in the right vector space. Polynomials can also be vectors, rational functions can also be vectors. And in the vector space of rational functions, we learned that any proper rational function can be written as a linear combination of simpler rational functions like this. So the PFD setup for this guy, and I know I haven't given you the rule yet, I'm showing you some examples, looks like this. I take my function and I write it as a over x plus b over x minus 1. What's going on here is I'm asking, where could this have come from? I know that if I add two things up that look like this, I need to have a common denominator, and that common denominator is going to be x times x minus 1, because that's the denominator of each of these pieces. So I'm asking, for what constants a and b, is it true that a over x plus b over x minus 1 is equal to 1 over x times x minus 1? That's the idea. Linear algebra guarantees that there are such constants. The question is, what are they? From here, I clear out the denominators. So I multiply both sides by x times x minus 1. On the left-hand side, I just get 1, because that's the numerator here. So when I multiply by the denominator x times x minus 1, that cancels perfectly over here, and I'm just left with 1. My right-hand side, if I multiply by x times x minus 1, I'll write it all out. Why not? A over x plus b over x minus 1 times x minus 1. I did that on the left-hand side, x times x minus 1 canceled. On the right-hand side, I distribute. When I hit the a over x with x times x minus 1, the x's cancel, and I get a times x minus 1. When I distribute that to the second piece here, the x minus 1's cancel, and I get b times x. My goal is to solve for the coefficients a and b. Those are the missing coefficients that I want. I want the constants a and b. So here a is a number, b is a number. I want to know what are those numbers. There's a bunch of ways to find them. This statement should be true for every value of x. So I could plug in some x values here. That might give me a way to find those coefficients. But the more general approach is to distribute everything. So here I had ax minus a plus bx, and then collect my like terms. So this is the same as 1 equals, well, my x's are ax plus bx. That's a plus b times x. And then I've got the only constant term is minus a. Come off to the side here and hang out with me for a minute. If I told you that 2x squared minus 3x plus 1 is equal to ax squared plus bx plus c, could you tell me what a is? Don't think too hard. It's got to be 2. There's no other way for it to work out. This would imply that a is equal to 2, that the coefficient here is the same as the coefficient here. Also, that b is equal to negative 3. And that c is equal to 1. The only way for two polynomials to be equal to each other for every real number x, in other words, the only way for you to have an identity between two polynomials is if all of their coefficients match. This is, again, coming from linear algebra. I'm going to apply that logic here. I think of my left-hand side as 0x plus 1. The coefficient of x on the left is 0. The coefficient of x on the right is a plus b. So this tells me that 0 has to be equal to a plus b. And the constant terms have to match. So 1 has to be equal to negative a. And this is a system of linear equations, which we can solve for a and b. So just to be clear about the terminology, this thing right here is what's called the PFD setup. This line and this line only, that's the PFD setup. And what I'm doing everywhere here is solving for the missing coefficients. And in this case, what I'm using is called equating coefficients. And there is another way to do that, which I will show you later, that can be faster, but doesn't always work. So the method I'm showing you right now always works. Let's finish it up. This tells me a is equal to negative 1, which I can put back in here. Right, my second equation here, 1 equals negative a, tells me a is negative 1. So I plug that back in here, and I get 0 equals negative 1 plus b. That means b is equal to 1. So I found my two missing coefficients. A is negative 1, and b is equal to 1. Now I return to the PFD setup. I'm going to rewrite my function, r of x, therefore, which was, remember, 1 over x squared minus x, which I said had to be the same as a over x plus b over x minus 1 for the right choice of a and b. A was negative 1, so this is negative 1 over x, plus b was positive 1, so this is 1 over x minus 1. And you can check, if you add those fractions, you will get 1 over x squared minus x. You have to have a common denominator, and then put them together, and it will come out to r of x. It will come out to 1 over x squared minus x. So what we just did is we found a way to undo the process of having a common denominator. We found a way to pull apart the pieces of that rational function. You'll notice I said the word linear algebra like 4 times. We're leaning very heavily on vector space theory here. It's okay if you don't know the vector space theory. I don't expect you to know it. All right? You haven't taken linear algebra. That's a class that usually comes 2 or 3 classes after this one. So don't stress. The big thing for us in this class is being able to get it done, being able to run the PFD algorithm and get out something like this. Why do I give a shit about this? If I wanted to integrate integral 1 over x squared minus x dx, if you look at this, this doesn't look anything like any of the integrals we've done before. I couldn't have done this using anything else. Trig sub won't work here. You could maybe complete the square downstairs and do a trig sub, but that would be so nasty. We saw one of those last time. So really, this is the way to go, because it gives me, without too much work, especially once I show you the little shortcut, I can rewrite the function in my integral like this. And notice that nowhere when I was doing the partial fraction stuff did I write any integrals. That's important. We step aside and do the partial fractions. It's a purely algebra thing. But while this would be very hard to attack directly, this is very easy to attack directly, because I was able to split my complicated looking rational function into some simple rational functions separated by addition. And that's the big deal. We go from something that involves like multiplication to something that's separated by addition. Integrals split up over addition. They don't split up over multiplication. So now I can do this as negative integral 1 over x dx plus integral 1 over x minus 1 dx. This first guy is easy. He's the natural log of the absolute value of x. And the second guy requires a little substitution. Z equals x minus 1. dz is dx. So he becomes integral 1 over z dz. So he also becomes a natural log term. This first piece is negative ln abs x plus this piece is ln absolute value z, which is x minus 1. And that's how you do that integral. The money step is here. And it's all done with PFD. So this went from being hella hard to hella easy through this little procedure. So what we're going to be getting good at is this procedure. That's 7.4. Okay, so I want to take a second for questions on this example. And then I'm going to show you the general PFD setup rule as simply as I can. And then we're going to work a couple more examples. Questions on these steps? Sure. Okay, so here was how it shook out. We did some algebra to rewrite our function like this. And that means if I wanted to integrate that function, I could integrate this instead because this function is equal to this function. While you're copying, I'll let my dog back in. Okay. So any questions on any parts of this? Any individual step here feel weird or we're uncertain about, or anything that's hard to read? So these problems, the integrals you get out are never too hard. The hard work is usually in finding these coefficients. And all that depends on is how complicated the PFD setup is. So the rules for the PFD setup are as follows. We break it down into a few different cases. Case 1, the denominator factors into distinct linear factors. That means you've got something like your numerator over your denominator looking like p of x over x minus, call them r1, x minus r2, up to x minus rn. So none of the factors downstairs have a power bigger than 1. They're all multiplicity 1 factors, meaning r1, r2 through rn are all distinct. if that's the case, then your PFD setup looks like this. I'm going to use an index here. So I'll say this is like A1 over X minus R1 plus A2 over X minus R2 plus all the way out to AN over X minus Rn. And usually we use letters A, B, C, and so on. But here, since I'm allowing there to be n different things and I don't have control over the size of n, I'll just say use the subscripts. This is the nice case. This is ideal. Case 2, the denominator has repeated factors. So that would mean like P of X over Q of X, the bottom factors, that's something like X minus R1 to the M1, X minus R2 to the M2, some horrendous shit like this, X minus Rn to the Mn. I'm using M here for multiplicity. If you have a repeated factor like that, then each one of these is going to get a bunch of different things. We have to build up. So your PFD setup there would look like A1 over X minus R1 plus A2 over X minus R1 squared plus, and you got to build all the way up to I guess I would call this A sub M1 over X minus R1 to the M1. And then to that, you would have to add, so all of this is just for this first factor. Then I would have something like B1 over X minus R2 plus B2 over X minus R2 squared. And I have to build all the way up to whatever this power is with these guys. So that would be BM2 over X minus R2 to the M2. And you have to do this for every single factor. Lastly, we would have something like C1 over X minus Rn plus C2 over X minus Rn squared plus all the way out to Cmn over X minus Rn to the Mn. So this is what I mean when I say writing out the rule looks scary. Here I'm just writing out one case of the rule and it looks scary enough. There is another case. There's actually two more cases. If your denominator has irreducible quadratic factors, that requires something special. And if your denominator has repeated irreducible factors, that also requires something special. But before we get to those, I want to show you what I mean by all this. So I want to grab a nice example. Maybe I'll just show you what a PFD setup for something like that looks like. The PFD setup for R of X equals, let's say 2x over x minus 1 squared plus or times x plus 1 cubed. If your denominator factored like that, then you have those repeated factors downstairs. The x minus 1 factor is repeated twice.
and the x plus 1 factor is repeated 3 times. That means this guy is going to get 2 different terms in the setup. The first term would look like a over x minus 1, and then maybe I would write b over x minus 1 squared. See, we build up to that power. And you have to do this. Why? Because a fraction whose denominator contains the square of x minus 1 could have come from something just looking like this, or it could have come from a combination of things looking like both of these. Then this guy is going to get 3 terms. So I'd write that as like c over x plus 1 plus d over x plus 1 squared plus e over x plus 1 cubed. So if you have repeated factors in the bottom, you have to build up to them. And you will have as many terms on the right-hand side in the setup as the number of repetitions of that factor in the denominator. Notice that the numerator has no effect on the PFD setup. As long as the degree of the top is smaller than the degree of the bottom, the numerator doesn't affect this process at all until you multiply out the bottoms and start trying to equate coefficients. I know that this sometimes takes a little bit of time to internalize, so I'm going to do one more example just like this, here where we combine the nice case and the unnice case. So the PFD setup for, maybe I'll let r of x here be 2x squared plus 3 over, and let's say x times x minus 1 times x plus 2 cubed. The first 2 factors of the denominator are not repeated. So they each just get 1 term. So the x factor, well, gets this. The x minus 1 factor also is not repeated. So he just gets the single term in the setup. But then the x plus 2 factor, he's going to get 3 terms. C over x plus 2, d over x plus 2 squared, and e over x plus 2 cubed. Feel like you understand how the repeated factors affect the setup? The number of terms you have here should always be the same as the degree of the bottom, meaning the sum of the multiplicities of the bottom. Okay. The next case, so we're continuing the cases. This would be case 3. The denominator contains irreducible quadratic factors. Something that we learn in pre-calc is that every polynomial can be factored into a combination of linear and irreducible quadratics. So remember, the degree of the denominator is, if you multiplied everything out, what would be the largest power of x down there? And that degree tells you how many terms in total there should be on the right. So if I multiplied everything out, I'm responding to a private question in chat. If you multiplied out the denominator down here, these 2 pieces would give you a quadratic. This piece would give you a cubic. If you multiply a degree 2 times a degree 3, you get a degree 5 polynomial. So the degree of the denominator here it's always the sum of the multiplicities. 1 plus 1 plus 3 is 5. So I expect to have 5 terms on the right. And then for each factor, its multiplicity, the number that that factor is raised to, the power that that factor is raised to, tells you how many terms in the setup will be associated with that factor. So the x here had multiplicity 1, so he's only going to get 1 term. The x minus 1 factor here had multiplicity 1, so he only gets 1 term. The x plus 2 factor had multiplicity 3, so he's going to get 1, 2, 3 terms. All right. So the next case we need to handle is what we do if the denominator contains irreducible quadratic factors. So if r of x looks like p of x over what's the right way to say this? I don't even want to write this out, right? So the general rule, just like the last general rule I showed you, is kind of scary. Those factors, irreducible quadratic factors, in the denominator get terms in the PFD setup with linear numerators. So I'll just show you by example. That's the easier way to do it. If I had 1 over x times x squared plus 1, x squared plus 1 doesn't factor. So this x term here, he's nice. No repeats, no irreducible quadratics in him. But this next guy, he is irreducible quadratic. And if I have to ask where could those have come from, those could actually have come from anything looking like this. And in general, if I had other irreducible quadratic factors, they would each get a term that looks like this. If I had something like this, for example, where I have 2 different irreducible quadratic factors downstairs, and it's important that you check that these are irreducible. If these aren't irreducible, you don't do this. Irreducible means doesn't factor over the real numbers, means that the roots are non-real complex numbers. If these do factor, then you factor them and you treat it as one of the previous cases. This would have a PFD setup looking like a over x plus 3 plus bx plus c over x squared plus 1 plus dx plus e over x squared plus 4. So irreducible quadratics downstairs are associated with terms in the setup that have linear polynomials upstairs. And then the last possibility is that you have repeated irreducible quadratic factors. And in that case, you kind of blend the two things. So case 4, the denominator has repeated irreducible quadratic factors. Meaning, if my denominator, if I had something like x plus 1 times x squared plus 3 all squared, like this guy is a non-repeated linear factor. This guy is a twice repeated irreducible quadratic factor. So here the x plus 1, I would just have the a over x plus 1 term. This guy, I would have bx plus c over x squared plus 3. And then dx plus e over x squared plus 3 squared. And if this was a cube, I would need a third fraction over here, like fx plus g over x squared plus 3 cubed, and so on. So case 4, you're kind of combining cases 2 and 3, where you have a repeated factor that you need to build up to, and that repeated factor is an irreducible quadratic, so each one of his fractions will get a linear numerator. Kind of seems unpleasant, I know. But in practice, you don't run into a lot of these. In fact, you run into these very, very rarely. So I want to show you one kind of worst case PFD setup, and then we will do some examples where we do direct actual computations. Okay. So what does a worst case PFD setup look like? It means I have all the nasty shit. It means I've got cases 1, 2, 3, and 4. So what does that look like? Well, if I started with something like x cubed plus x squared plus 1 over x squared times x minus 1 times x squared plus x plus 1 times x squared plus 1 cubed. The first thing we should do is ask, are there any shared factors between the top and the bottom? But here there are not. Factoring the cubic upstairs is a little bit gnarly, but I'll ask you to trust me. There are no shared factors here. That's always something you should check, right? Always factor the top and the bottom if you can. What do I have all together? This guy is going to give me 2 terms, and they're each just going to have a constant upstairs because he is a linear factor that is repeated twice. This guy is a linear non-repeated factor. This guy, I need to ask, is he irreducible? Because it's not obvious right away that he is. This guy is irreducible. So we know he's going to contribute 3 terms, each with a linear numerator. The PFD setup for this is a over x plus b over x squared. Those are both coming from this guy. This guy will give me a c over x minus 1, and he only shows up that one time because he's a linear factor that's not repeated. To figure out if this is irreducible, I need to compute b squared minus 4ac. That's the easiest way to do it. The discriminant, that's 1 squared minus 4 times 1 times 1, that's negative 3. Since the discriminant is negative, he is irreducible. So he's going to contribute 1 term over here with a linear numerator. And then this piece is going to contribute 3 terms. No, very sweet. But I'm teaching right now, okay? Sorry. So the x squared plus 1 cubed would give me an fx plus g over x squared plus 1 plus hx plus I over x squared plus 1 squared. And then a last term there, jx plus k, sorry, my cat's making an appearance, over x squared plus 1 cubed. Kitty cat, come here now. You can't be up there, baby, not right now. I know. You're very sweet, you're very cute, everybody loves you. All right, it's okay, why don't you go upstairs and cuddle with mama? Sorry. All right, this is about as bad as anything you could ever imagine. I would never give you something like this. I would never make you find all these coefficients. But it's important that you understand how the setup works, and looking at a worst case is a good way to understand that. So before I go to concrete examples, any questions about where any of these terms in the PFD setup are coming from, why they are the way they are, that sort of shit. Okay, so I'm going to go ahead and run through one concrete example. We're a little short on time. That involves some of this extra work. I know that we're going a little bit over time. My previous class went a little bit over time, so I'll ask you to hang in with me. Nala, kitty, get down. No, kitty, no. If I wanted to do the integral 2x squared minus x plus 4 over x times x squared plus 4, I recognize that the integrand is a rational function. The degree of the top is 2. The degree of the bottom, if I multiply this out, the degree is 3 down there, you can see. So it is a proper rational function. So I step aside from the integral and I set up the PFD. That means I write down just my function, no integral, and the PFD setup. Remember, the PFD setup doesn't care about the numerator, it just comes from the denominator. So this would look like a over x plus bx plus c over x squared plus 4. Then I clear the denominators. So on the left-hand side, I'll have 2x squared minus x plus 4. And on the right-hand side, if I multiply by x times x squared plus 4, the x's here will cancel, and I'll get a times x squared plus 4 plus bx plus c, and don't forget these parentheses, fractions are grouping symbols, times x. Now I'm going to distribute everything out over here and combine my like terms, then equate the coefficients. So this is the same as 2x squared minus x plus 4 equals ax squared plus 4a plus bx squared plus cx. And then I collect my like terms. My x squareds are ax squared and bx squared, so that's a plus b times x squared. My constant term, my linear term, my x term is just cx. And then my constant term is plus 4a. And now this is just like that thing I asked you at the start, right? If I have like 2x squared minus x plus 4 equals some stuff on the right where I don't know, since I've got all of my x's grouped together, all of my x squareds grouped together, and all of my constants grouped together, I know that 2 has to be equal to a plus b. I know that -1 has to be equal to c. And I know that 4 has to be equal to 4a. That lets me set up a system of linear equations. A plus b is equal to 2. C is equal to -1. And 4a is equal to 4. And I'm writing it like this to remind you that this can be done with matrices. Right? This is a plus b plus 0c, 0a plus 0b plus 1c, 4a plus 0b plus 0c. So you could solve the resulting linear system using what you remember about matrices. However, this linear system is easy to solve. Since 4a equals 4, I can get a right away. A has to be 1. Also, this guy told me right away that c is -1. And if I plug this back here, that tells me a plus b equals 2 is the same as saying 1 plus b equals 2, which is the same as saying b equals 1. So I have no kitty, no Nala, sweetie, no, 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 no. A equals 1, b equals 1, and c equals -1. So now I have found my missing coefficients. So I return to my PFD setup. Kitty cat, you gotta move. You gotta move. I'm sorry, baby. I know you don't want to. I know you don't want to. You gotta go though. So I return to my PFD setup where I said 2x squared minus x plus 4 over x times x squared plus 4 is equal to a over x, don't hiss at me, plus bx plus c over x squared plus 4. That must be the same as, well, a was 1, so this is 1 over x, plus b was 1, so that's just x, plus c is -1 over x squared plus 4. And only now do I return to the integral. Therefore, the integral of 2x squared minus x plus 4 over x times x squared plus 4 dx is equal to the integral of this. And I'm going to split up the integral. Actually, first I'm going to split up this fraction here, the x minus 1. So this is 1 over x plus x over x squared plus 4 minus 1 over x squared plus 4 dx. The 1 over x integral is easy, but I'll write it out like this so we can see where everything's coming from. All right, this will be a natural log. This will require a little substitution. This will require a trig sub. This is going to be an arctan. And the way you get there is by letting x equal 2 tan theta. Dx would be 2 secant squared theta d theta. In this guy, we're going to let z be x squared plus 4. dz then is 2x dx. And this one is easy. He's just the natural log of the absolute value of x. Kitty cat, I swear if you jump up here. So what do I get? I have ln absolute value of x plus, when I do this substitution in this integral, my denominator is just z, and my numerator x dx is 1/2 dz. So I'll have plus 1/2 integral 1 over z dz minus, here, my trig sub, I have 2 secant squared theta d theta from my differential. And then the denominator, x squared plus 4, that's 2 tan theta squared plus 4. So that's the ln of x plus 1/2 ln of z minus integral 2 secant squared theta divided by, that denominator is 4 times tan squared theta plus 1 when you factor the 4. Tan squared theta plus 1 is secant squared, so that will cancel with the numerator. I'll write the ln of z here as x squared plus 4 because that's what z was. And this guy becomes 2 secant squared theta over 4 secant squared theta. That's just the integral of 1/2 d theta. So finally, we get here, integral of 1/2 d theta is just 1/2 theta. I'm sorry, kid. I know you want attention. And theta is the inverse tangent of x over 2. Remember, x was 2 tan theta, which means x over 2 was tan theta, which means the inverse tangent of x over 2 is theta. So your final answer here is ln abs x plus 1/2 ln abs x squared plus 4 minus 1/2 inverse tangent of x over 2 plus c. And this is about an average difficulty problem. We had 3 constants to solve for, and the linear system wasn't hard to solve. We were able to read off A and C right away, and then we were able to get B by substituting those values into the first equation. Once we had our PFD all worked out, we had to do this integral. And we do this integral by splitting each piece up and integrating each one on its own. First guy was easy. Second guy was a little u sub, a little z sub. Third guy was a little trig sub. I'll show you a formula for integrals like this in general. It's not hard. But that's how it shakes out. The miracle of partial fractions is that it will let you integrate literally any rational function. No limits. You can do whatever you want. Because every rational function is made up of polynomials. Every polynomial can be factored into linear factors and irreducible quadratic factors. And you know how to set up the PFD for any combination of those things. Peter asked a good question. Could we have run PFD again on this integral? You could, but it would just give you this thing back. This is as simple as this gets. Because it is a proper rational function, yes, but there's only one factor in the denominator, and it's that irreducible quadratic factor x squared plus 4. So you certainly could set it up, and you would just find that this coefficient is 1 and this coefficient is -1. We wouldn't get anywhere new. So because there's only one factor in that denominator, PFD wouldn't get us anywhere. PFD is only useful if you have multiple factors in the denominator. Yeah, Caesar asks a good question. What if the rational function is not proper? So we mentioned that at the very start of class. If the rational function is not proper, then you need to long divide. We can only do PFD on proper rational functions. And if you have an improper rational function, you can always long divide, and that will give you a polynomial plus a proper rational function. So see the module thing that I'm going to add to Canvas today for a reminder on how to do long division. And if you look at the examples in the textbook, right around page 498, 499, they do a few in there where you have to long divide first. I think there is 1 or 2 problems in homework 5 that requires you to long divide first, but that's the game. If it's not proper, if your rational function is improper, divide the top by the bottom and then see what you get. You may get a polynomial, that would be dope. If you don't get a polynomial, you'll get a polynomial plus a proper rational function, integrate the polynomial, and then do PFD on the proper rational function. So this is a lot to go over in one day. I fully acknowledge that you may want to rewatch this video. You may want to watch it on like half speed or 3/4 speed. I do have to switch over to my office hour now, so if you want to talk about other stuff, I am going to end this meeting and go over to the office hour because I might have students from my other class waiting. I hope you've enjoyed this. I strongly encourage you to read the textbook on this section and then to also rewatch this video. MIT, the open courseware folks, also have a really good video on partial fractions. So I'll post that to Canvas, but you might want to Google around and see if there are other videos or things that you might want to watch before you dive into this part of the homework. All right, remember, homework 4 really needs to be done today. And then homework 5, you want to get a good chunk of that done over the weekend, if not all of it. Next Monday, I'm going to talk with you guys about some tricks to allow you to do some of this partial fraction stuff faster. The integrals are what they are, but the PFD stuff, there are some tricks that will allow you to find those coefficients faster. That's usually where most of the time goes. So on Monday, we'll talk a little bit more about PFD. Wednesday will be a review for the test. And then on Friday, we won't have a regular class. We'll have the test instead. So in a little bit here, I'll have some detailed instructions on the study guide and the exam up on Canvas for you. I'll also post some tricks for PFD stuff and a few other lectures that I think you might find useful. And if you would like to talk a little bit more, come on over to the office hour starting now. All right, I hope you guys have a lovely rest of your day. If you need any help or anything at all, don't hesitate to ask, okay? All right, see you.